Hey everybody, welcome back. It's Morgan here, and we're going to be talking today about the last two pages of the electrochemistry lecture outline. And what this really represents is a debriefing, or you could even use it as an introduction to a lab that we were supposed to do, where you determine the concentration of hydrogen peroxide via redox titration. Now, redox titration typically is not a 1-to-1 ratio. So it's not like most acid-base titrations where the moles of the acid and the moles of the base are equal and the stoichiometry is really straightforward. So you'll have different ratios. One of the very common titrants that we use is potassium permanganate, and people sometimes refer to that as the purple juice. There was actually a pretty long period, about 20 years, where both the AP Biology and the AP Chemistry exams had redox titrations that required potassium permanganate. So you had multiple exposures to it. So the reaction that we're dealing with is the permanganate ion in an acidic solution forming the Mn2 plus ion. So we end up having 4 H2Os on that side and 8 H pluses on this side, and that's going to be 7 to 5 electrons between them. Okay? Now, as with any titrant, you need to standardize it. You need to react it against a standard. And in this case, I always liked to use sodium oxalate or even oxalic acid, but something that gives you the oxalate ion, which is going to give you 2 carbon dioxides and 2 electrons. So you can go through a standardization there, okay? You need to keep it acidic, so you would typically add 3 molar H2SO4 just to have it be acidic, and you'd skip an indicator because it turns out that permanganate's purple and the Mn2 plus is a pink color. So you could just tell by adding drops of the purple stuff, they would turn clear immediately upon reacting with oxalate. And the pink would really not be concentrated enough to show up. But when you add a drop of the purple and you do have a color left over, usually a light red pink type thing, you realize you have some excess permanganate. So the indicator itself is built into this titration. It's really slick and smooth. So now, after the standardization, you go to determine the concentration of H2O2, which is going to give you oxygen, a couple hydrogen ions, and 2 electrons. Now, the standardization is typically carried out at a higher temperature, about 50 degrees Celsius. So we would have been titrating on stir plates with heaters built in. But then the peroxide reaction cannot be carried out at the higher temperature because the H2O2 would be decomposing on its own. But you'd still need to add the acid to keep it an acidified species. Okay, so overall, our reaction for the standardization would be 16H plus 2 permanganates plus 5 oxalate ions to give us 2 Mn2 pluses and 8 H2Os and 10 CO2s. You typically would not see bubbling for the CO2. It's not being produced in a high enough concentration. Okay, so this is what a typical data table might look like. Let's figure out the volume of KMNO4 that's used. So we take the 58, let's clear that out, 58.48 minus 1.23, which is 57.25. So I'm actually going to write it as 0.05725, and that's going to be in liters. 58.26 minus 1.26 And exactly 57, wow, okay, 0.05700 liters. And then 59.02 minus 1.32 and 57.70, so 0.05770 liters, okay? Now, for the moles of the sodium oxalate that we use, we're starting off with 5.5736 grams Na2C2O4, 1 mole of the Na2C2O4 has a molar mass of 134.00 grams, spot on, Na2C2O4. And that's going to equal. Now we're also going to end up doing the same thing for 5.7285 grams and 5.7955 grams. So this first one comes out to be 0.041594 moles. The second one, 0.04275. And the last one, 0.04325. So this one, 0.041594 moles of the C2O42 minus times. And downstairs we put 5 moles of oxalate for 2 moles of permanganate. It's a 2-to-5 ratio. So we end up with 0.016638 moles, 0.0171 moles, and 0.0173 moles. Okay, now equals 0.016638 moles was the first one. And what we will do with that is actually divide it by the volume for that trial, 0.05725 liters. And that equals 0.05725. No, let me run that again. That was that. So that 0.2906 molar. And then for this one, it was 0.3000 molar, nice and spot on, and 0.2998 molar. So when it is averaged, you get 0.2968 molar permanganate. Okay? So leave that there for you for a second. I'd actually like you to run these numbers through your calculator and just make sure you can get all of them. So now we have the standardized concentration for the permanganate, and what we can do is go on to the next step here, where we are going to do the actual determination of the concentration of the peroxide itself. 5H2O2 plus 2MnO4 minus plus 6H plus ends up giving us 2Mn2 plus 8H2O and 5O2. Okay? So, again, we would take a look here at our titration data and the difference between the final and the initial volumes. 5.88, so 0.00588 liters. And then for the next two, I've got 0.00549 liters and 0.00510 liters. Now, how do I get the moles of KMnO4 present? What I have to do is start off with the concentration, 0.2968 moles per liter of the permanganate. Multiply by 0.00588 liters, and then, well, actually, leave it. Let's just do that as the moles at that point. And that gives me 0.00175 moles. And doing the same thing for the next two, 0.00163. And then for the third one, 0.003775. I'll do sig figs down at the end. So I can take that number at this point and say the 2 moles of the permanganate for 5 moles of the H2O2. And what I get is 0.004375 moles, 0.004075, and 0.003775. Now, that's the moles of the actual peroxide. Remember, it's a solution, so there's a lot of water and stabilizers and other stuff that's in there. So to find the mass of the H2O2, I'm not interested in the mass of the solution. I'm interested in the mass as determined by moles. So I take my 0.004375 moles of H2O2, and then down here 1 mole H2O2, and 34.02 grams of H2O2. Okay? So that's going to give me moles. And what I come up with is, or I'm sorry, I said that wrong. That's going to give me the mass of H2O2 from moles. 0.149, 0.139, and 0.128 grams, okay, for each of those. I'm limited to 3 sig figs based on these volumes. So now for the percentage, what I do is I take my 0.149 grams of actual H2O2, and I'm going to divide it by the mass of the solution, and in each case, 10.00 grams times 100%, which gives me 1.49%, 1.39%, and 1.28%, which averages out to 1.39%. Okay? So I'm going to be posting a link to a video to show you what this actually looks like. It's only a couple minutes long, nothing to worry about there, so that you can see the kind of fascinating way how the permanganate functions not only as the titrant but as the indicator, so that you don't need to add something like phenolphthalein. It wouldn't work. I mean, because you're adding acid, you're keeping this in an acidic environment the whole time, so there's no way to measure an endpoint based upon a change in pH, but the color change does beautifully. Okay, that's the end of the electrochemistry lectures. There'll be some homework problems going along with that. I hope you all are having a good day, and once again, this is Morgan signing off.